All right, here we go. This is Forces Assessment 2A. This is a little kind of let's go over this kind of thing. So what we have here to start is, first question says, if a baseball with a small mass and a bocce ball with a large mass are dropped from the same height, at the ground at the same time, they have the same acceleration. How is it possible that balls with different masses follow the same acceleration? Well, if you think about the fact that you have a small ball and a big ball, the Earth pulls this one down with a small force, the Earth pulls this one down with a big force. But because this one is more massive, it has more inertia, more resistance to change in motion. So it's resisting change in motion more, which means in order to get to accelerate, you'd have to pull harder, which is what happens with the Earth. So the Earth pulls down harder on more massive objects, but they're also harder to move. You can also think about it this way. The acceleration is equal to either small force over small mass, or if it's a bigger object, it's big force and big mass, but you still have the same acceleration. Second one says, inertia is the property of matter. Define inertia. It's the term we give to the natural tendency of an object to resist change in its motion. So all objects resist change in their motion, and it turns out that more massive objects resist change more. So that's the same thing we saw up here. And so a bowling ball is harder to get rolling than a basketball. Not because it's heavier, because it's more massive, it resists change in its motion more. Okay? This says, in the space, draw and label the force diagram. No problem. So that's the dot, it represents that cart. That's the force from the Earth on the cart. Let's say it's on a table. And let's say there's some string pulling it or whatever. You could just say pull or string or whatever. So there's a good force diagram. It says, what can you conclude about the motion? And you conclude that the car will accelerate because the forces are unbalanced. If we look at the next one here, it says, what we're going to do now is we're going to take the same cart and we're going to pull it with twice the force. So what happens to the acceleration? Well, you're going to get twice the acceleration because the pulling force doubles. Right? And we know there's a linear relationship between the unbalanced force and the acceleration. Next one says, let's go back to the original cart and we're going to double the mass. So if you double the mass but keep the force the same, the acceleration is going to be half that of the original, right? Because the mass is doubled and there's an inverse relationship between mass and acceleration. Twice the mass, half the acceleration. This last one I really like because what you're going to notice here is you're doubling the force and you're doubling the mass. And so what ends up happening here is that the acceleration is going to be the same as the original because we're using this acceleration equals unbalanced force over mass. And if you do times 2 the force and times 2, it's still equal to the same acceleration on top and bottom. This one says, here's our Volkswagen here, and here's our little bug here. Okay, so we got a 1,200 kilogram Volkswagen moving along when it hits the bug, and the bug splats on the windshield. Which applies more force, the bug on the windshield or the windshield on the bug? And according to Newton's third law, we call these Newton's third law force pairs. The force of the car on the bug is equal to the force of the bug on the car. Now, the car pushes the bug to the right and the bug pushes the car to the left. So one of these is negative because they're left and right. But this is what Newton's third law says, that all forces come in pairs that are equal in strength and opposite in direction. So even though the bug splats, the forces are the same. So here we go. So let's do this next one. So it says draw a force diagram. Start with a dot. I can see that the Earth is going to pull it down. All right, this is the force of the Earth on the block. And that's 15 newtons, and I know that because it's a 5 kilogram. I see that this hand is pushing it down and to the right. So it's pushing it to the right and down. So this is 26 newtons. And if I track the triangles, it turns out that this is a, ooh, what was that? Five, 12, 13. So since I have 13 and 26, that's times 2. So this is 10 newtons here, and this is 24 newtons here. Now, those are things we know. What else? It says the frictional force between the block and the surface is 14. So I know that's 14, that's here. And the surface has to push up also. So we have 50 down from the Earth and 10 down from the hand. And so what are we getting here then? So this is 60 newtons, and that's the force of the surface on the block. So I got the labeling. I got the values, I'm feeling pretty good about that. It says, what can you conclude about the forces? Are they balanced or unbalanced? Well, the 10 and 50 balance out the 60, but I have 24 to the right and I have 14 to the left. Therefore, I would say that the forces are okay. Forces are unbalanced, and you can get that from the force diagram, and so you could say not enough friction, or some proper justification. This one, I don't know why this one's orange. That's weird. So this student pushes this student. What happens? Well, during the pushing, this one's going to move this way, and this one's going to move this way. So they're going to move apart from each other. Even though this guy's doing the pushing, he's definitely going to go back. And so the students will move away from one another, but B is going to move faster than A. Which has a larger acceleration? B has a larger acceleration because they have less mass. We talked about this earlier. Less mass is less inertia, less resistance to change, so easier to move. And how does this all work out? Well, the forces of A on B and B on A are equal. And we know that again because they're Newton's third law force pairs. The force of A on B is equal to the force of B on A, but in opposite directions. All right, I hope that helps. Let me know what questions you have.